This is the first question that I've been sent, and it says, find f composed with g of x for the indicated functions and simplify. We have f of x equals 6x plus 2, and g of x equals 4 over x plus 2. So we have to first find f composed with g of x. This operation of composition means substituting one function inside of another function. So it means that we're going to substitute g of x into f. So we're going to take this g of x, this expression, 4 over x plus 2, and we're going to substitute it in for the x that we have in f. So that's going to give us 6 times 4 over x plus 2 plus 2. And this is f composed with g, but we also want to simplify. So to simplify, I'm going to start by treating this 6 as a 6 over 1. And when we multiply fractions, we multiply the numerator times the numerator and the denominator times the denominator. That's going to give 24 over x plus 2 plus 2. And I want to continue to simplify this so that we have one fraction. Now when we add fractions together, we need to have a common denominator. So currently we don't have a common denominator. We have one denominator of x plus 2 and another one of 1. So I'm going to multiply the fraction with a denominator of 1 by x plus 2 over x plus 2 so that I can get that common denominator. That will give 24 over x plus 2, and I'll distribute the 2 in the other fraction. That would give 2x plus 4 over x plus 2. And now that I have a common denominator, I can combine these into a single fraction. And in the numerator, I have 24 plus 2x plus 4. I have some like terms in the numerator. The 24 and the 4 will combine together to be 28. And that gives 2x plus 28 over x plus 2. So that's our simplified composition, f composed with g. Okay, so here's another question that I've been asked. This question says, to use the quadratic function, f of x equals 5x squared plus 10x minus 6, to address the following. We want to find any x-intercepts and find any y-intercepts of this function. I'm going to start with the y-intercepts, even though that's part B. So to find a y-intercept, you let x equal 0. So we're going to substitute a 0 into our quadratic function. That would give 5 times 0 squared plus 10 times 0 minus 6. And 0 squared is 0, times 5 is 0, 10 times 0 is 0. Carry down that minus 6, and 0 plus 0 minus 6 is a negative 6. So we have a y-intercept of 0, negative 6. Then we're going to look for our x-intercepts. To find an x-intercept, we let y equal 0. We're using function notation, so f of x is the same thing as y. We're going to set f of x equals 0. And that's going to lead to the equation 0 equals 5x squared plus 10x minus 6. So this is a quadratic equation. And there's probably more than 4 methods, but 4 that I typically teach for solving quadratic equations. There's factoring, There's the square root method, completing the square, and the quadratic formula. Factoring and the square root method are methods that don't always work. Not every quadratic can be factored, and not every function, not every equation is written in a form where the square root method can work. But they're typically easier methods to use. The other two methods, completing the square and the quadratic formula, those methods do work on every single quadratic, but they can be a little bit tedious. So I typically take the approach when solving a quadratic equation to try to factor first, or if it's possible to use the square root method first. And if those methods don't work, then I go to the quadratic formula. So if I were to start this with factoring, and by the way, I've already ruled out the square root method, because with the square root method, you have to have your b term, your middle term, gone. So you can only use that square root method if you only have the square, not the square and the linear term. So factoring is the one I'm going to try. And if I were to factor my front of the factorization, the first terms in the binomial would need to be a 5x and an x, so that it would multiply to be 5x squared. For the second terms in each binomial, they would need to multiply to be 6, and we have a couple choices there. It could be 2 times 3 or 6 times 1, so I'll try both of them. So 2 times 3 would give me 6. And then I need to check to make sure that I would get the right middle number of 10. So I would check multiplying the inside and the outside. That's a 2x and a 15x. And if I combine those by either adding or subtracting, that's not going to give me the 10x in the middle. So I know this is not going to work. So then I try something else. I try the 3 over here and the 2 here. So that would give 3x and 10x. 3 and 10 are not going to add and subtract to give me 10x, so that's not right. So let me try the 6 and the 1. I'll try 6 and 1. That's 6x and 5x. That doesn't give me 10. Let's try the 1 and 6. 1 and 6 gives me x and 30x, and that doesn't give me the 10x in the middle. So factoring does not work here. We've tried every combination, and factoring doesn't work. So now I'm going to go to trying the quadratic formula. So with the quadratic formula, I would let a equal 5, b equal 10, and c equal -6. The quadratic formula is x equals -b plus or minus the square root of b squared minus 4ac all over 2a. I've got -10 plus or minus the square root of 10 squared minus 4 times 5 times -6 all over 2 times 5. So I'm going to use order of operations to simplify. So inside of the radical, I'm going to apply the exponent first. 10 squared is 100. And 4 times 5 is 20, and 20 times 6 is 120. That's going to be a plus. And 2 times 5 is 10. Let's continue this up here. We have negative 10 plus or minus the square root of 220 over 10. And now I want to simplify the radical. When you simplify the radical, you would like to have a factorization of 220 that contains a perfect square. And you want that because the square root of a perfect square will simplify. So looking at 220, let's do this work on the side. So looking at 220, there are lots of different factorizations of 220. 1 times 220, 2 times 110, 4 times, let's see what, 55, 5 times 44. Six is not going to work. 7's not going to work. 8's not going to work. How about 11? 11 times 20. And I'm trying to think if there are any more. 20 is 2 times 10. Yeah, we skipped 10. So I skipped 10. 10 times 22. But all of these, if you look at all of these, there's only one of them with a perfect square. 4 is a perfect square, which is 2 squared. So that's the one we want to use so that we can actually simplify the square root. We've got negative 10 plus or minus the square root of 4 times 55 over 10. The square root of 4 is 2, and 55, since it's not a perfect square, will stay underneath the radical. We can't perform that operation without a calculator. I'm sure somebody can perform it without a calculator, but not me. The final thing that we want to do here is that we have a fraction, and you always want to write fractions in lowest terms, no common factors between the numerator and denominator. And so looking in the numerator, I have 10 and 2, and both of those are even, divisible by 2, so we have a factor of 2 in the numerator. And in our denominator, we have a 10, also has a factor of 2. So I can factor a 2 out of the numerator. Oops, sorry. So if I factor a 2 out, this becomes negative 5 plus or minus square root of 55 over 10. And now the 2 and the 10 can cancel. 2 goes into 2 one time, 2 goes into 10 5 times, and that's going to give us negative 5 plus or minus square root of 55 over 5. So this is an acceptable answer for us. However, some people do like to write this as, instead of one large fraction, 2 separate terms. So if you write it as separate terms, you would divide the 5 that's in the denominator into both terms that you see in the numerator. So you would write negative 5 over 5 plus and minus square root of 55 over 5. That would give you negative 1 plus or minus square root of 55 over 5. So this is also an acceptable answer. If you guys are doing this in my math lab, it will mark you correct on either one of these. So on this question, we want to find the equation of all horizontal asymptotes, if it has any, of this rational function. We have the rational function f of x equals 5x squared minus 3x cubed over 4x cubed plus x squared minus 6x plus 5. So this is an algebra class, and when we're finding horizontal asymptotes using algebra, what we're doing is we're using a set of rules that have been summarized for us using calculus, limits at infinity. So we have to go back to what are our rules surrounding horizontal asymptotes before we can find those. So all of the rules that we have involve knowing the degree of the numerator and the degree of the denominator. And once you know the degree, we call n the degree of the numerator, and we call m the denominator degree, and we compare them. We have 4 different comparisons that we focus on. N is less than m, n is equal to m, n is equal to m plus 1, and n is equal to greater than or equal to m plus 2. So these 4 different scenarios are that the first one is the numerator is smaller, numerator is less. The second one, we have the numerator degree equal. The third one, we have the numerator degree being 1 more. And the last one is where the numerator degree is 2 or more. Or I like to just generalize it and say a lot more. So we need to figure out which case we're in, and the horizontal asymptote is described in each one of these cases. So let's figure out which case we're in, and then I'll describe what our horizontal asymptote is in each of these cases. So in our function, we want to pay attention to the highest power on our x from the numerator, and that's a 3. So the degree from the numerator is going to be 3, and that's our n. From the denominator, the highest power on x is a 3. And our degree from the denominator is 3, and we call that m. So that puts us in the second scenario where the degrees are equal to each other. So when the degrees are equal to each other, the horizontal asymptote is going to be y equals the ratio of the leading coefficients. Now the leading coefficients are going to be the coefficients that match those highest degree terms. So we have -3 being the leading coefficient from the numerator, and 4 being the leading coefficient from the denominator. And we're going to take the ratio of those. The ratio means fraction. We have -3 from the numerator and 4 from the denominator. So our horizontal asymptote is y equals -3/4. So that's for the second case. If we were in the first case, our horizontal asymptote would be y equals 0. And in these 2 cases, there is no horizontal asymptote. So anytime the numerator is larger, there is no horizontal asymptote. So here we have a question coming from our chapter on applications of quadratic functions. And it says an object Just a second, my whiteboard's not working. There we go. An object is launched vertically in the air at 46.55 meters per second from a 10-meter tall platform using the projectile motion model. H of t equals negative 4.9 t squared plus v naught t plus h naught, where h of t is the height of the projectile t seconds after its departure. V naught is the initial velocity in meters per second, and h naught is the initial height in meters. Determine how long it will take for the object to reach its maximum height, and what is that maximum height. So we're given this quadratic function, and this quadratic function is a model of the height t seconds after departure. So our model, h of t, is negative 4.9 t squared plus v naught t plus h naught. So I want to fill in from the word problem the values of v naught and h naught. V naught is the initial velocity, and h naught is the initial height. So we're given here in the word problem that this object is launched from a 10-meter platform, so that's our h naught, the initial height. And we're given that the object is launched at 46.55 meters per second. That's our initial velocity. So let's substitute those values in. We have h of t equals negative 4.9 t squared plus 46.55 t plus 10. So now we have our model for the height. H is height, and t is time in seconds. And then we're going to read our question again. Determine how long it takes for the object to reach its maximum height, and what is the maximum height. So we want to know the maximum height and how long it takes to get to that maximum height. So this function, remember, is height. So if we're looking for the max height, we want to look for the highest this function can be. This function is a quadratic function. And so we can think about the graph of a quadratic function. So height, we know, is a quadratic function. And what do we know about the graph of a quadratic function? It's going to be a parabola. And there are only two ways that we can draw a parabola that's a function. We can draw it like this, facing up, or we can draw it like this, facing down.
But since the negative coefficient will be facing down?
Because that leading coefficient of A is negative 4.9, we know that the parabola is going to be this one here, the down-facing parabola. And remember, we're looking for the maximum height. That maximum height is going to occur at the vertex. So we're going to be able to answer our question by finding the vertex of this quadratic function. We do have a formula for finding the vertex, and this can be a little bit confusing here. We have h is what we usually call the x-coordinate of the vertex, and our height is labeled as h as well. So this h that I'm drawing here is the x-coordinate of the vertex, and that formula is negative b over 2a. So our a is negative 4.9, our B is 46.55, and our C is 10. We have negative 46.55 divided by 2 times negative 4.9. I'm going to get my calculator. So we have 2 times 4.9 is going to give us 9.8. We have negative 46.55 over negative 9.8. And this works out to be a positive 4.75. So this is usually our x coordinate, but we don't use x in this equation, we use a t. So this number, this 4.75, is our time in seconds. So it's going to take 4.75 seconds to reach the maximum height of that object. And then we can find that maximum height by plugging in the 4.75 into our function. And this h is the height h. This one was the vertex h. This h is the height. So we have negative 4.9 times 4.75 squared plus 46. Let me give myself some more space so this is not crowded. We have negative 4.9 times 4.75 squared plus 46.55 times 4.75 plus 10. That's negative 4.9. And 4.75 squared is 22.5625. Then I need to do 46.55 times 4.75. And that is 221.1125. I need to do 4.9 times 22.5625. I get negative 110.55625. And do 221.1125 minus 110.55625. And that gives me 110.55625 plus 10. That is 120.55625. And I don't see any mention of rounding. It might be where you enter your answer. But if I were to round this to one decimal place, that would be 120.6. So this object reaches a max height of 120.6 meters at a time of 4.75 seconds. For this question, we want to graph the function f of x equals x plus 5 times x plus 3 over x squared minus 36. So this is one of our rational functions, and I really want to know where the asymptotes are occurring. So I'm going to start by factoring the denominator. That denominator is a difference of squares, and it factors into x plus 6 times x minus 6. Now, based on that, I know that this rational function is going to have discontinuities at x equals negative 6 and x equals 6. So I'm probably using a word that belongs in a calculus class there. We usually say restricted value instead of discontinuity. So if I substitute a negative 6 and a positive 6 into this rational function, it's going to be undefined. Now these restrictions produce in the graph either a vertical asymptote or a whole removable discontinuity in the graph. And I don't know which one it is unless I have my function factored out the way it is right now. So when you have a common factor, you're going to have a removable discontinuity, but if you don't have a common factor, you have a vertical asymptote. So since I don't have a common factor of x plus 6, that means that the restricted value of negative 6 is going to be a vertical asymptote. And there's no common factor of x plus 6 in the numerator either, so x equals 6 is going to be a vertical asymptote as well. So no common factors, no whole or removable discontinuity in the graph, but we do have two vertical asymptotes. So then I'm going to look for horizontal asymptotes. And horizontal asymptotes are found when we pay attention to the degree of the numerator and the degree of the denominator. So the denominator degree is going to be a 2 because that's the highest power on x, and we call that m. In the numerator, we have a function that's factored, but if we were to multiply this out, we would end up getting an x squared. Maybe I should write that in black. If we multiplied this out, we would get x squared plus 3x plus 5x plus 15, and that highest power on x from the numerator is a 2 as well. So we have a degree of 2 in the numerator, which we call n. Once we've identified the degree of the numerator and denominator, then we compare them to each other. So in this case, n is equal to m, and we have memorized that when the degree of the numerator equals the degree of the denominator, we do have a horizontal asymptote, and that horizontal asymptote is going to be y equals the ratio of the leading coefficients. Now, our leading coefficient here is the x squared, and it has a coefficient of 1. And our leading term in the denominator is x squared, and it has a coefficient of 1. So ratio of 1 over 1 is 1. So this rational function has a horizontal asymptote at y equals 1. Now, some other information that might be helpful would be x-intercepts and y-intercepts, and we may need some additional points on top of that as well. So looking for a y-intercept, I would let x equal 0. That would give f of 0 equals, we can use the factored form, 0 plus 5 times 0 plus 3 over 0 squared minus 36. So that is going to be 15 over negative 36. And we can reduce that. 3 goes into both of those. 3 goes into 15 5 times. 3 goes into 36 12 times. So we get a negative 5 over 12. Then when I'm looking for x-intercepts, I let y equal 0, or in function notation, I'm setting f of x equals 0. And that gives x plus 5 times x plus 3 over x squared minus 36 equals 0. This looks initially pretty messy to solve, but if we multiply by the denominator on both sides, that's going to cancel out from the left, and then on the other side we have 0 times x squared minus 36, so we get a 0. And we can set each factor equal to 0. We get x equals negative 5 and x equals negative 3. So we have x-intercepts of negative 5 and 3. Now I think I'm getting closer to being able to sketch a graph of this. So let me get my coordinate plane here. And let's write down some of the things that we've gotten. We have vertical asymptotes at negative 6 and positive 6. So that I'm drawing the vertical dashed line at negative 6 and positive 6. We have a horizontal asymptote at y equals 1. And we have x-intercepts at negative 5 and negative 3. And we have a y-intercept at negative 5 over 12, which is kind of a small number, so about right here. And I have quite a bit of information to draw the graph in between the two vertical asymptotes, but no information to the left and to the right. And what I need to know is whether my graph will go to infinity or negative infinity. So whether you're going to have your graph above your your horizontal asymptote or below, and same thing over here, whether it's going to be above or below. So I'm going to pick a test point, let's say negative 8 and positive 8, and substitute it in so I can see what's happening to the graph in those areas. So f of 8 is 8 plus 5 over 8 plus 3 over 8 squared minus 36. So that is a positive times a positive over a positive, and that's positive. So that tells me that my graph will be in this positive part over here. And then if I try negative 8, it's going to be negative 8 plus 5, negative 8 plus 3 over negative 8 squared minus 36. This is a negative times a negative over a positive, which is a positive. That tells me my graph will be up here. And when I'm sketching that part of the graph, what I'm doing is I'm following the vertical and horizontal asymptote as guidelines. And then in the middle, I'm going to connect these 3 points. I can do better than that. So it'll probably go something like this. But I'm going to check one more thing to be sure. I want to check to see if this graph crosses the horizontal asymptote. So I'm going to check this right here. I'm going to see if f of x ever equals 1. That's my horizontal asymptote. So x plus 5 times x plus 3 over x squared minus 36. Let's see if that equals 1. And that is x plus 5 times x plus 3 equals x squared minus 36 if I multiply by that denominator on both sides. Can multiply this out and I get x squared plus 3x plus 5x plus 15 equals x squared minus 36. I'll combine like terms. That gives 3x plus 5x, that's 8x. And I'll subtract x squared on both sides. That gives 8x plus 15 equals negative 36. Subtract 15 on both sides. And that gives 8x equals negative 51. Divide by 8. And x equals negative 51 over 8. Let's see what that is approximately. So 6 3/4, 6.375. Negative 6.375. So, what does that mean for our graph? Okay, I want to do one more test point. So I'm going to erase this right here and do one more test point. And I want it to be in between negative 6.375 and negative 6. So maybe negative 6.1. Negative 6.1 plus 5, negative 6.1 plus 3 over negative 6.1 squared minus 36. So what does that come out to be? That's going to be a negative times a negative over a positive. So I still get a positive. Is that this graph comes down like this, touches that, and then goes like that. So after thinking about this graph a little bit more, I have adjusted how I've drawn the curve on the left-hand side a little bit. And I thought a little bit more about why I was having trouble graphing this piece. And I think it's because I only focused on whether I had a positive or negative here instead of getting the actual y values. And if I had the actual y values, I would be able to see whether the graph went below that horizontal asymptote and came back to it. So I'm going to spend just a couple minutes actually finding the y values of these extra points and draw a better sketch of this graph. And so we're getting a y value of 5.1 when we have an x of 8. So make sure I type that in right. Negative 8 plus 5 times negative 8 plus 3 over negative 8 squared minus 36. So we have about 0.5 for that one. That's really, really helpful for me to see that that is below 1, because that means it's below the horizontal asymptote. And we have 2.81. So once again, this is really helpful for me to see that this is now above 1, which is above that horizontal asymptote. So I've already redrawn this graph considering those pieces of information, but let's put in the points that we have there. -8 and 0.5 is about here. We already mentioned that the graph crosses that horizontal asymptote at -6.35. And then at -6.1, 2.8, we have that other point. So I can see here that the graph crosses that horizontal asymptote and then it's going to come back to the horizontal asymptote. And now I feel much more confident about how I've drawn that graph. Thank you for checking out my videos. Have a great day.